Okay, thank you. Yeah. Okay, thank you. So I got about 30 seconds, so hang on to your seats. That's all I'm saying. So yeah, I'm Paul Williams, Principal Development Engineer. Alan's shown you the problems, and I'm going to talk about a couple of the solutions now that we've come across and we've been investigating in ACCSEAS. These are the two big novel results from ACCSEAS as far as resilient PNT is concerned. The ACCSEAS receiver, we believe we've built the world's first prototype multi-source resilient PNT receiver. It's based on GNSS or GPS as a primary source. It's got integrity algorithms in it and a terrestrial backup. So that's frequency and system diverse. So that gives you that complementary backup system. Michael's going to talk about R mode. So we've got something, where's my laser? Something in the ship and something outside the ship, some infrastructure. Michael and his team have been investigating this R mode, adding ranging signals to differential GPS broadcasts and AIS. And we'll hear more about that later on. But as far as the receiver is concerned, this is where we start. This is the IMO architecture diagram for ship-side resilient PNT. And you can see on the left-hand side here, we've got various input components. So we've got our GNSS receiver, our primary source, our DGPS receiver, so maybe some other radio navigation receivers, other systems like the gyro, compass, speed log, rate of turn indicator. They all produce data. Whether they produce position, velocity or time or raw data, all of that data is fed into this thing, a PNT data processor element. And that's really the heart of this system, because that does all of the data analysis, the performance monitoring, and actually makes the decision as to what single source that we output. What's the best PNT source? What's its integrity and accuracy? And what are these alarms that we need to tell the mariner, that there's a problem, that things are going on here. We've got various options for providing resilient PNT, and when we started, we looked around and saw what was available. And you can harden existing systems. So GNSS and GPS, you can use adaptive antennas that do clever nulling of interference in the direction of interference. Plausibility checks, again, clever processing, parallel processors and integrity algorithms. We could use inertial navigation systems, and depending on the quality and how long you want that inertial system to take over for, if you lose GPS, then you pay much more money for it. So we want to do something perhaps that's a little bit more, certainly in the short term, a bit more accessible. And so we kind of concentrated in ACCSEAS on this, in this sort of domain, using dissimilar services, radio navigation services. So we looked at radar absolute positioning, we looked at ranging mode, and as I say, Michael will talk about that in a minute, and we looked at ELRAN. But what we wanted to do with ACCSEAS was to demonstrate the concept. So in actual fact, you only kind of need one, maybe two systems with which to demonstrate this principle, and we'll see that in a little while. So I'm going to talk about each of these systems just very briefly, just to give you a flavour for what we've been doing. We've been looking at radar absolute positioning. A radar normally is used to get situational awareness and relative position, so you can see what's happening outside the ship. but modern technology has allowed the development of what are called e-raycons. Now, a raycon is something that you can attach to, say, a bridge stanchion or put near where there's shallow coastline to make those structures show up better on your radar. A raycon responds to a radar paint by transmitting its own radar signal, and that paints a Morse character on your radar screen, and that shows you the distance and the orientation to the raycon. But you can have, but modern technology has developed these e-raycons. So this Morse signal can be modulated with data, and that's typically either the raycon's ID or its position. If you know the position of the thing that you're measuring range and bearing to, you can get the position of your ship. And so what we did back in 2012 was a trial where we installed two e-raycons at each of two of the GLA lighthouses, and we did some experiments. We had an enhanced radar on one of our vessels, and we were able to measure range and bearing to each of the raycons. And in general, if you measure range and bearing to one raycon, you get about 40 meters position accuracy. So you get a latitude and longitude out of it, but it's about 40 meters accurate. So 40 meters accurate when you're within about 5 nautical miles of the raycon, and 100 meters accuracy when you're about 12 nautical miles. So the accuracy and performance depends on how far you are away from the coastline. If you get range and bearing from 2 raycons though, you get a bit more information. And where those 2 lines of position cross, I don't know how to work this thing, you end up with more information, and you end up with a little positioning ellipse where you're now, originally you could be along this line or you could be along this line. If you know both of them, you're somewhere in the middle. And we got 2 meters positioning accuracy within about 10 nautical miles from the coast. So that's radar absolute positioning. R mode, Michael's going to talk about that. That's basically adding ranging signal to the IR, the DGPS broadcast, so 300 kilohertz signals, or AIS as well, so VHF signals. And Michael's going to talk about that. ELORAN, we have ELORAN in the North Sea region operating for a number of years, and where you've got things like differential LORAN and propagation data, you can get 10 to 20 meter positioning accuracy in the North Sea region today using the LORAN transmitters that are around Europe. So those are the 3 systems that we've investigated in ACCSEAS, and those 3 systems are kind of in various states of development. This is the ACCSEAS planned multi-source receiver architecture. This is, if you remember our IMO architecture, we've now got an architecture for the receiver we're doing in ACCSEAS. So you've got some various input services like the signals in space, propagation data. And these are the sensors that we are considering building into the receiver or catering for should these systems be developed further in the future. So we've got our GPS, our GNSS receiver. That's good to go. We've got GNSS, it works most of the time. We've got our ELORAN receiver. We can do ELORAN. R mode, that's in development. We've done a feasibility study. Michael's results are excellent, and that's on the horizon. And our radar positioning, although we've done a trial, we are not in the position yet to actually get a radar positioning module into the receiver, but we can take input from anything in the future. So if radar, in the next project, perhaps if we develop radar absolute positioning, we can feed that into the receiver, and we can use the data processing module in there as a platform to process it and to use it as part of resilient PNT. Each of those outputs data, either raw or processed, and then we've got this clever PNT data processor that analyzes each of these systems' data, makes the decision about the best quality, detects GPS interference and switches, and this is the output then, which is then connected to your ECDIS, and all of that equipment that Alan showed you that needs a latitude and longitude on the ship's bridge. This is what it looks like. It's a black box, 19-inch rack unit. It's got lots of connectors on the back, and it's got lots of pretty coloured lights on the front. It's like Christmas all over again. It's fantastic. And this is what it looks like on the bridge of a ship. This is actually the equipment room behind the bridge of the P&O Pride of Hull ferry. So this is a ferry that operates between Rotterdam and Hull. It comes with its own monitor and keyboard. It's got a computer in it. But of course it's designed to be connected to an ECDIS and to provide information to the mariner. And that's what we did here in this trial. This is the EPD, the e-navigation prototype display running on a laptop developed by the DMA. So we can output our resilient PNT, feed it into the e-navigation prototype display and use that for positioning. This is what it looks like inside. There's ELORAN receiver, DGPS radio beacon receiver, of course GPS receiver, various interfacing hardware, power supplies, 2 antennas, a GPS antenna and a combined ELORAN and radio beacon antenna. Now this is where, so we've got GPS and we've got ELORAN, but this is where we're also thinking about future arm mode. There's a spare processing channel in this receiver that can be adapted and used for arm mode. And the receiver, of course, is the antenna is sufficiently wideband that it can receive both LORAN and DGPS R mode signal. So it's R mode ready. That's the buzz phrase we use. So there's a computer on board as well, a small form factor PC, and now I've really broken this because I have no laser. So let me just get my backup. Always have a backup. That's the moral of this presentation. So there's a single board computer, and there's some software running on OEM receiver monitor control software, some bespoke software which controls each of the receiver receivers and switches ports on and off. And this is the heart of it. This is our PNT data processor. This was written in MATLAB. It's the heart of the software. This is the clever stuff that does the decision making about what to output from the unit. I do need this. I can't just throw it away. No, I really have broken it.
Well, you're running out of time. Anyway.
I know, and I'm stuck.
So it doesn't help you, my friend.
Can somebody click my slide, please?
I can offer you this, but it will not.
There we go. How much time have I got?
It depends.
Okay.
Did you split with Michael even?
I think I was supposed to have 10 or 15, and you were supposed to have 7.
You still have to negotiate.
We can negotiate that. I mean, I'm going to talk. This will be shown in the workshop anyway later on.
You have 2 more minutes.
2 more minutes.
And then Michael will have.
Okay, that's fine. So it does. So the PNT data processor is very clever. Does all this stuff. Next slide, please. That's if you're a geek, then you're interested in graphs. This is the GPS processing. So this is the early version of the PNT data processor. It does some GPS analysis. There's the ELORAN stuff, looking at all the ELORAN signals. And then this is the decision-making part where you're deciding whether to output GPS or LORAN, and there's some positioning error information, this positioning error ellipse. Next slide, please. Show us some pictures of ships, Paul, for God's sake. Well, here's the Pride of Hull P&O. There's our receiver on board, some antennas. And this is a ro-ro cargo and passenger vessel, 60,000 tons. And this is where this is the ship on which we ran the demonstration, and the DMA showed all the e-navigation services, and we demonstrated the receiver, and there's a video you can see all of that happening in the workshop later on. Next slide, please. This is what the e-navigation prototype display looks like. This chart, and then there's a resilient PNT panel, which the DMA put on, implemented, that you can see what's the source of your positioning, whether its integrity is good, what's its positioning error. Next slide, please. We zoom in, you can see that under normal situations we're running GPS, it's okay, it's got about 3 meter horizontal protection level error. You can plot the error ellipse on the outline of the ship so the mariner can get an idea of his positioning error. If GPS is lost, you get an alert, and the mariner can click on that alert, and he's told that the source has changed. You then, at the same time, you're swapping sources, and this is swapping to ELORAN, and again, the processor analyzes ELORAN to make sure it's okay and everything's good. Next slide, please. More ships, Paul. Okay, here's a ro-ro cargo, 25,500 ton vessel. The Euroship, this is the Euroship Palatine. They're very much interested in getting a receiver on board, and we're integrating one of the ACCSEAS receivers into the ECDIS on the bridge. So they have 2 inputs into their ECDIS, currently both served by GPS receivers. Now that's fine, you've got redundancy. If one of those GPS receivers fails, you've got the other input to fall back on. But what if you've got a system-wide GPS failure or a regional failure? So what we're doing is we're feeding the ACCSEAS receiver output into the second ECDIS input. So if they lose GPS over a wide area, they've got at the moment an ELORAN fallback, and they can continue to deliver their cargo. Next slide, please. JHV Patricia, one of our buoy tenders. Again, we're putting an ACCSEAS receiver on board, integrated into the ECDIS, and Sperry themselves have modified the ECDIS to include a resilient PNT panel. So manufacturers are getting on board, they're getting interested in using the system and coming along with this. The receiver, we haven't just thrown this receiver on board and said get on with it, guys. You know, we've had it EMC tested, electromagnetic compatibility tested. MCA and Lloyds have had a look, and we've got it certified. So it doesn't interfere with any other systems, and systems don't interfere with it. Next slide, please. Yeah, this is what Alan was talking about. We're concentrating on integrating the ECDIS. We're not actually integrating with any other ship systems yet. We want to get it into the ECDIS so that you come to fix my stuff. Thanks. We're not integrating into any other system, just the ECDIS. So the marrow can actually see the positioning output and give us feedback and information about how it's performing. You can't really see that if you're feeding it into, you know, your satellite broadband system or your vessel data recorder. So we're concentrating on the ECDIS. Next slide, please. So it's a prototype. We're aware that there are standards being developed, you know, the IMO, the IEC test standards, and RTCM. The prototype we've got, the ACCSEAS receiver we've got, is a good starting point. And I think when you see it working in the demonstration and in the workshop, and you actually see the output and what it can do, and based on the feedback we're getting from the mariner, I think you'll agree that it's a good start. And I think that's me done. Next slide, please. Yeah, thank you.
I try already to start, and I would like to thank, because everything what happens over the ACCSEAS project is a teamwork, so I would like to thank everybody who contributes to the ARMOD, and therefore many thanks. And I will give a brief overview about the ARMOD and our results. And so first, the ARMOD. What is the idea? It's a transmission of an accurate synchronized timing signal from existing terrestrial radio infrastructure. And within the maritime area, we have two systems which are identified, which are globally distributed and which are known in the maritime field. This is the MF Yala radio beacon service on the one hand, and on the other hand, we have also the AIS shore-based service. So within ACCSEAS, we provided a feasibility study whether to look and have a detailed investigation on various systems. So we looked in the part one in the MF Yala radio beacon service. Then we looked into the AIS potential of using that for the ARMOD. And in the final part, we used a combination of all together. Here's a result out of the feasibility study. We see here, this is more or less the accuracy figure, showing that with a typical signal reception, we could achieve 3 meter, and with a weak signal, we are in the range of 10 to 20 meter. And on the right hand, we see a picture showing in the black triangles are radio beacon sites which are already existing in the North Sea area. And the blue area, more or less, is the representative geometry which we could achieve using the MF radio beacons as it is. And we see we have already a very good basic system because the geometry is very good. Also, the performance with respect to accuracy is very encouraging. And here we see also a day-night effect, and you see that the potential to provide a 10 meter or 10 to 20 meter accuracy system is quite good. Just a brief result about our findings for AIS. Again, we have an accuracy figure which is depending on the signal strength and the signal quality, and we are also varying between 5 to 6 meters up to 100 and 200 meters depending on the signal quality. In that case, we we investigated about existing infrastructure in the North Sea and also in the Baltic Sea area, taking into account AIS shore infrastructure from our Danish colleagues and also from Denmark and the existing German infrastructure. And you see here also the result is quite successful in a range of 10 to 20 meters, but in that time a little bit closer in distance to the sea, because we have a different radio system providing not that large coverage area. And also, if we are taking into account all the elements, so using MF radio beacon, AIS, and also ELORAN, we see here an interesting picture, because here we have the density plot, which was already shown in the baseline and priority report. And you see that with the existing infrastructure, we could already provide a 10-meter accuracy backup system in the areas of the highest interest where the ships are driving. Okay, the next step then was to build up really and do a validation of the theoretical findings, and we set up a real transmitting site in the Netherlands, in IJmuiden. And so by putting together an armored modulator and a transmitting system with an antenna, we could already provide a real armored system on the MF radio beacon. And we put also a receiver together at the monitor side, and here we use the lighthouse tower in Noordwijk. So this is a picture of the prototype receiver and an atomic clock which we use. And with that equipment, together with the transmitting side and the fixed receiver side, we could really do first measurements. And we started with that measurements at the 27th of January. So it's really something which we produce very up-to-date results. And this is just a picture of the signal which we provided. So it's the typical MSK signal to provide the DGNSS information together with continuous wave signals which are used for the armored signal in it. And so having that together, we are able to really do first measurements. And these measurements have been performed over the last weekend and analyzed over the last week. So what we here see is really first measurements of an armored signal. And you see here, these are the phase measurements over a time period of 2 days. You see the day period and the night period, which is a little bit more noisier. And we did the measurement on the two continuous wave signals, and you see that it's very encouraging that we could achieve accuracy in a better than 5-meter domain. And I think this is very good and nice results out of this very last finding. And so I come to the conclusions, Mr. Chairman, so just 30 seconds, I think. And so first, I would like to say that armored is a backup system which can really meet resilient PNT requirements of e-navigation. And to achieve a widespread resilient PNT, the best solution is really to use all signals which are available in a really true all-in-few receiver, and that it's more or less what the colleagues have just presented. And a first on-air test on the armored using the MF radio beacon signal is really very encouraging, and it validates that the results and the findings from our feasibility study. And it's really, I would like to make that point, it's very important that we have some capability to continue our work on the armored, because we really just started. We have now the equipment together, we have a receiver, and it's really necessary to do the next steps on that. And I hope we get some budgets. And this ends my presentation. Thank you very much.